My name's Sebastian, and today I'm going to speak about debugging, as the title says. And debugging is a very important subject that I don't think we... Sorry, you can't hear me. I hear something. 1, 2, 3. Better? Okay, now I hear myself less, but they hear me more. Okay, so I'm going to talk about debugging today, because I think that's a very important subject that we don't talk about that often at C++ conferences. And I don't know about you, but I at least spend probably more time debugging than doing actual programming. So who's this talk for? Well, there are basically two audiences here. It's of course a good talk for people who are just starting their career in C++ and they want to figure out something about debugging. But it's also a good talk for those who have been doing this longer. Somebody told me once, your talk was a good reminder of how we should do things. So maybe you're more in that category. Then I hope you also take away something useful from that talk. So if we want to start debugging, we first have to find a problem, right? Our big goal here is to ship software that is as free of bugs as we can make it. So first of all, we have to notice that our software has a problem. And first of all, before I come to that, we have to specify what we're talking about. So what is a bug? What are we looking for here? Well, we could say that our program has some kind of specification, right? Usually that is implicit. It's something you and your colleagues have some shared idea of. And in some rare circumstances, it's actually a formal specification maybe that is written down. And now, of course, our program has a bug if its behavior does not conform to that specification. And what we get usually is not a description of the bug. It's just some user feedback, some bug report that describes a symptom of a problem. Something is wrong, but we don't know what yet. And so we have to make sure we get as many of those bug reports as we can to find the important problems. So this is a bug report. This is a bug report I received 15 years ago, and more than 15 years ago. And you can see I remembered that one. Because clearly, it is not a very good bug report, right? It's very unspecific, and maybe it also has some problems with attitude. But I remember I could help. I could help that person. Generally, we want to get better bug reports than that. And there are a couple of ways which we can achieve that. Maybe our application crashes. That can be good. It's at least a clear signal that something has gone wrong. Maybe you get a core dump. Maybe you get an error message, a line in a log file, or some other kind of observable misbehavior. Something doesn't look right, maybe, in your application. And we want to know when that happens. And specifically, we want to notice when that happens only on a client computer. It's easy if it happens on my machine. I can just look into what's going wrong. But what happens in your case when that occurs only on a client's machine? Do you notice all these kinds of bugs? Are you notified somehow? So that's the problem we have to solve first. There are a couple of ways we are notified of bug reports. So we are programming in a type-safe language. So our first defense against bugs is actually the compiler. We get type checks. These are bug reports if they fail. We can help the compiler along a little bit by writing good static asserts. They will notify us of things that are probable bugs. We can evaluate more things at compile time by using const expert. Who knows what class of bugs that would eliminate if we do a lot of compile time calculation? What kind of bugs can const expert evaluated statements not have? UB, very good. So there was even a talk at cppcon a few years ago where people wrote a microkernel, I think, in const expert statements. So it didn't have UB. Of course, after compilation, we want to do automated tests. Maybe you have a QA department. Hopefully you have one. They do more tests. They can give you good error reports. But inevitably, you will ship software that still has bugs. And you have to find out if your program does something wrong at runtime. So what we do at ThinkCell, for example, is that we have a very strict error checking policy. So we check all the API return values for whatever API you call, and we would always distinguish between expected and unexpected return values. So let's say you call create file. Create file can always return you don't have the privileges to create that file. That is probably an expected case that you have to handle. It would be very surprising if create file suddenly returned error out of paper. And if it did, I would certainly want to know. But I'm not going to handle that case in my code. I don't know what to do if create file doesn't have enough paper. So that might send a bug report to our backend. We also use asserts a lot to assert preconditions and postconditions, and we also report if they fail. They will also stay in release builds, so we get all these assert checks in release builds as well. So what we're trying to do here is we're trying to make sure that all the invariants in our code are enforced, and we want to be notified when one of those invariants is violated. There's a whole talk by Arno, who's also here, about our approach to error handling, if you're interested in more details. So this is how the backend looks. We would have some database where all these bugs appear, where we can filter them by operating system they occur on, by version of our build, by line in the code where they occurred, etc. And this is extremely useful to get notified of bugs that depend on a specific environment configuration. So typically we find bugs this way that we could never reproduce in-house because they only occur if you have a very specific, I don't know, antivirus tool installed, for example. Okay, so now that's the first step. You need to get as many bug reports as you can. Now you get one of those. Maybe it's a colleague calling you over and say, hey, I have this problem here. One of the asserts you've written has failed. You don't know nothing else about that bug. How often does it occur? How can you reproduce it? You don't know anything. Is it worth it to look at this single occurrence? Is it worth it to have a development process in place where a colleague can just call you over and say, hey, I have this problem. I think you've written that. Can you look at it right now? Because I don't know if that will ever appear again. And I would argue it's very good to have such a development process. There's this famous quote here by Gordon Ledwin, 1 in a million is always next Tuesday. And what he meant originally was that computers had become so fast by the time he wrote MS-DOS 4 that even a situation that had only a chance of 1 in a million of occurring, well, it would occur by next Tuesday. Here it's the same. So maybe that's your lucky day and you have a chance to look at a very rare problem, a bug you will never see again, a bug that is hard to reproduce. But maybe it would have an easy fix if you would just look at it now. And you can be sure that when you ship your software to 1 million customers, that problem will occur 1,000 times. Well, what can you do without knowing anything? Well, you can think about it for a moment. Maybe you can form an hypothesis on the cause of that bug. Maybe you can improve your error reporting, enforce stricter invariants, be notified earlier when you have some idea what could have gone wrong to end up in such a situation. Maybe there was an assert missing earlier. So that's the least you can do. But there are cases where that is your only chance to actually fix a problem. And here I have my first little quiz to make this a bit interactive. I brought my best bugs. These are all the bugs I could fit on a slide. So here we are doing a little HTTP request. And we are doing an asynchronous HTTP request where we have some delegate thing which will get called. So here on new data is going to get called when the HTTP API says, I have new data. Then we take a lock, set some internal state. Did we actually have data or did we receive an error? And then we notify the main thread who has been waiting for us. Now the main thread is pretty lazy and actually does all this synchronously. We don't care for the async part. So the main thread will also just wait on the condition variable. It will wait until that state flips to error or data. And well, if it's an error, then we'll throw an exception and exit that thing. So this is this is going to crash. 1 in a million times, maybe. And it's going to crash when doing that notify all, but very rarely. Anybody has an idea what the problem could be? Yeah. Sorry? The lock guard here? No, I think the lock guard is fine, I think. Yeah. Here? No, that lock will be locked when the condition variable flips. One other suggestion before I solve this little bit. Huh? It's very subtle. It is a spurious wake up. Who here knows what spurious wake up means? Ah, not so many people. Good, good. Spurious wake up means that this condition variable we are waiting on might wake up at any time. It might wake up before we call notify all. Specifically, it might wake up exactly here, when we flipped that state, but haven't called notify all yet. And in that situation, this condition is already true. We're exiting, we're checking if this is an error, and if it is an error, we're throwing an exception, and we're going to destroy that poor guy. And then it's going to crash. And this is something we actually wrote, because it looks so good, right? Doing the notify all outside of the mutex looks like it would be correct, because you want to release the mutex. But it is actually, in that very specific circumstance, it's actually wrong. Which is why the C++ coding guidelines explicitly tell you to write the notify always inside the mutex. Because these situations can happen, and then they're extremely hard to figure out, right? So now that we've done got so many bug reports, we've looked at the simple problems that we could figure out by taking a hard, deep look at them. But in most cases, we're not so lucky. We have to start to debug the problem. And that is a lengthy process, right? An iterative process, where you first get a report, then you think about it a little bit, you form an hypothesis, what could be the problem, you test that, you're wrong, you think again, form another hypothesis, until you finally really figure out what the problem is. And then you can proceed to fixing it. And we will cover all these steps on the following slides. And here it's important to do this right and not to do it too fast, to jump to conclusions. Because otherwise you're never going to find the real problem. And if you're doing this inefficiently, with the wrong tools, or without having a good plan, you're going to be really grumpy in front of the computer, because this is going to take a long time. So what are the strategies we have to make this quicker? What is the plan we should formulate? So the first thing we need, if we want to repeatedly test the bug or our solution to it, is of course a good reproduction, right? We want to repeatedly analyze the same situation, so we have to reproduce the issue. And making a bug is not either reproducible or irreproducible. There are a lot of shades of gray here. So in the best case, the bug is always reproducible in debug builds on any machine with an interactive debugger attached. But we might not be so lucky. In some cases, and in the worst cases, maybe it's only sometimes reproducible on very specific machines with very specific compiler settings, and the bug disappears if you attach a debugger, for example. So we want to make, as a first step, we want to make all our issues more reproducible. We want to make them appear more often. And there are a couple of techniques we can use to achieve that first. So if a problem is only sometimes reproducible, then we can use the sanitizers. Who here uses the address sanitizer regularly on its code? Who here knows what address sanitizer does? Also, good. A lot, but not all people. Still not all people. So the address sanitizer will instrument your code. So let's say a very frequent bug that is very easy to write is that you write code that creates a temporary variable, and then that temporary variable is destroyed, but you still hold a reference to it and still access it. Right? People not do it. Did you make that mistake already? You probably, everybody did. So that often works, because if the memory has not been reused, then the old data is still in the same memory location, the access still works. You don't notice the bug until something changes, and then suddenly it crashes. What the address sanitizer does is it instruments your code, and it will make sure that that bug, that memory is reused immediately, and it writes some magic pattern in there, so that the bug will always appear. It will always tell you, you have used an out-of-scope temporary in this location. So that's extremely useful. If bugs are only sometimes reproducible, very often that might be a timing issue. Maybe you need to run it in a specific order on a machine that has a specific performance for the bug to appear. Often those issues will disappear if you attach an interactive debugger as you're trying to figure out what goes wrong. The bug is irreproducible. What you can do in those situations is write stress tests, for example. Make sure that the piece of code where you think the bug is executed much more frequently than it would otherwise be, to make sure this bug appears soon. Maybe if attaching an interactive debugger doesn't work anymore, you can write data to a log file, figure out what is happening that way, and still reproduce the bug. Or you can wait for the problem to appear and then write code to diagnose the state your system is in. That can also be a good technique. Writing code to debug issues is often a technique we can use. Sometimes those bugs are only reproducible on some machines. So it's a good idea that this maybe has something to do with those specific machines, and we want to gather all the information we can about those machines. What operating system are they running on? What CPU? What's the version of your software? The version of all kinds of other softwares? Anything that could interfere with your application might be interesting. If you're writing desktop software, which I think most people aren't anymore, then this is especially relevant because desktop environments are super hostile. There are virus scanners, system tools, the administrator can do things wrong, the user rights management can be off, there's digital rights management software, all kinds of things that might interfere with your application. Maybe you can reproduce the environment in a virtual machine once you figure out what the relevant parts are. Maybe that's very hard. You can reproduce it on a client machine instead. Or, in the worst of all worlds, you can have the client ship an identical machine to you. Maybe that's something your client images. The admin department will create identical machines, and they can just send one to you. But here it's important to keep an open mind. Whenever you're trying to find a bug, it's important not to jump to conclusions. It can always be anything else. It could still be a timing issue, for example. Maybe the machine you're looking at is very fast, or it's very slow, or very busy, or something else. And if everything else fails, then hopefully you have a good automatic bug reporting system, like I've shown in the beginning. You can also use Google Crashpad, for example. There are open source solutions to do that. So you'll be notified when that bug happens on machines of other clients, for example. And maybe you find one who's more cooperative, where you can find out more, etc. You can also try to ship analysis code. If you have a bug that is especially difficult to analyze or don't find out what the problem is, you can build an analysis code and ship it in your running software. And if you're very good and have a very strong bug reporting system, you can even ship fixes that you try out. We did this once, I think, for one especially hard problem, where we wrote a fix where we thought it might work and then had the error reporting report back to us if it worked or if the bug was still there. And sometimes, unfortunately, all you can do is look at your program state after the problem occurred. Maybe look at some output your program produced and figure out from there what the what the problem was. And we also have that. So here's another little quiz. We had a customer report who said that starting our software failed, and according to the log files, it threw in bad alloc exception. Now we could look into our bug reporting database and found out, hey, this actually failed when loading the settings files. So we couldn't reproduce it, of course, but we could get the customer to send the settings files because we knew where the problem was actually occurring. So we could look at those. And it turned out that in those settings, where we store some number formatting data, there was some bogus data. Instead of a string that should be there a single time, it was there 2 to the power of 18 times. Too much for our poor vector. So we thought, well, maybe something doubled this data structure, like 18 times. So you go deeper and you look, that's a vector. So we have a vector that is a pair of a size t, and that format string. So this would be maybe an index into a string and some number format that you want to insert there. So now comes the crucial information. That thing is stored in shared memory. And that memory is shared between different processes, of course. Does anybody have an idea already? Oh, what could be the problem? We didn't either. So you think, well, the vector size, what is that? Well, it's the size of the vector in bytes divided by the size of that data structure, this pair of size t and format. Anybody? Anybody seeing it? So that vector is shared between 32-bit and 64-bit processes. Oh God, yeah. That was not clever, right? So that failed, of course, because size t doesn't have the same size, right? So what was the fix? That's something I mentioned in the very beginning. The fix, apart from changing the size t, was writing a static assert. Writing a static assert in our code with the hard-coded value of the size of that shared data struct to make sure that whenever we compile it for 32-bit, for 62-bit, for whatever, it had the exact same size in bytes, so that this bug will never happen again, hopefully. Okay, now we have a good reproduction. We can look at the bug as often as we want. Now we have to actually find where the problem is in our code, right? Because typically, the symptom we observe, the crash, is not where the bug is. The bug might have happened somewhere else in our code. It might have happened somewhere earlier. We're just seeing the results. So we have to walk back somehow. And I'll say it again. We can use all those sanitizers to help us do that. We should use interactive debuggers to do that. Not all people do that. But there are a couple more techniques we can use to get a quick idea of where the problem is. So first of all, we might want to gain an understanding of how this larger system works. Maybe we're not so familiar with it, or maybe there's just a lot going on and we want to know what happens in what order. And the good old solution was here to do printf debugging. So you would insert printf statements somewhere and then look at the log and try to figure out what happens. And that has a big downside. That requires recompilation, and it's much better to use tracing breakpoints. Who here uses tracing breakpoints? Good. So tracing breakpoints are breakpoints that are supported by all the big debuggers that don't interrupt the execution, but they will write data to your error output. So more specifically, they can write arbitrary strings, but they can also write out the variable values you want to look at. So it's like printf debugging, but much, much better, because you don't need to recompile your code, and you can add them even to operating system functions. You can add them to arbitrary locations in the binary code if you want to. So they can do strictly more than printf. And GDB and LDB are so powerful that when such a breakpoint is hit, you can also make the debugger print a stack trace. So you can not only find out what is being called, you can also find out by whom that was called. That's a very good technique. And you can even script those with Python. to create breakpoints when breakpoints are hit or something. I haven't used that. Again, those breakpoints, because they use the debugger, might make some timing-dependent bugs disappear. And then you unfortunately actually have to use printf debugging. If all we're interested in is the interaction between our software and the operating system, there are much better tools we can use. We don't have to insert breakpoints everywhere we're interested in. There are operating-specific logging tools, of course. There's the process monitor on Windows, there's dtrace on macOS, there's strace, and a lot of other tracing tools on Linux. And if we want to understand the interaction between our tool and the operating system, then unfortunately we have to learn a lot about our operating system. And that's a thing that can take a significant amount of time when you're starting out to be a developer, to figure out how things work on Windows, on Linux, on macOS. How do file logs work, for example? Yeah, so that unfortunately takes quite some time and is very important. What you can also do is sometimes you know that a bug wasn't there in a previous version 2 weeks ago, and now it's there. And you can maybe use git bisect to find out which commit in your source repository introduced the behavior you're seeing now, the bug you're seeing now. That's a very important technique because that can help you understand what you were trying to achieve when you introduced that bug. And that's a moment where you can look at both things at the same time, right? You were probably trying to solve some problem, created a new one. Now you know the new one and the old one, and maybe you can find a solution to both problems at the same time. If you don't do that, then you run the risk of reintroducing the old one and doing infinite circles of this game. So that's often worth doing. Sometimes you don't have any clear idea of where that bug is suddenly coming from, but you have a working version and a broken version. You can step through both of them in parallel in debuggers, see where their behavior differs. You can also work through the code and try to disable code and recompile and see what you have to do to make that program disappear. It's also something I've already done. That requires knowledge of your code base, of course. It requires recompiling. It can be very time-consuming. It can also be the quickest way. It's very hard to say in advance, right? That's often the challenge when we're trying to do this. And one of the best techniques, if you're working through code, looking for a bug, maybe that is old code or code that you're not so familiar with, is improving that code. Maybe you're thinking through that piece of your program, and maybe you're the first one for a long time who's thinking that through. Maybe you think of new invariants that you think should hold, but nobody documented them. Maybe you can put them in as asserts. Maybe they won't hold, and you learn something. Maybe they do hold, and you just improve the code base. For very complex checks, you can do that just while debugging. And if you have especially old code, legacy code, maybe you can actually introduce better programming techniques. You find out, oh, I have some memory issue here, and this is all using raw pointers. You can introduce smart pointers, and you will probably not only solve the problem you're looking for, but a couple of others you haven't even found yet. And then there's also reverse debugging tools. I think there's one in the corner. WinDebug can do that, Undo can do that, and there's also RR on Linux. And these do exactly what we are trying to do here, right? They record a trace, and they can probably tell you better than I can. They record a trace of your execution until the bug appears, and then you can step backwards in time. So that can be exactly what we are trying to do here. And then I've mentioned it a lot of times, but it's very important to know your debugger. Like, it's always important to know our tools, right? And in that case, the tools are a debugger. Know about tracing breakpoints and about data breakpoints. Data breakpoints let you interrupt the execution when a specific piece of data, of memory, is accessed, if it's read or written. And we'll also see like one example when that is very useful. You can script those debuggers And I think it's also a very important debugging technique to have at least passive assembly skills. You don't need that often, but there are problems you cannot solve without being able to read disassembly. So for example, when you're trying to figure out if something is actually a compiler bug, it very rarely is, but it happens. And the only chance typically to find that out is to look at the disassembly and look, is that correct assembler code for what I've written in C++? So here we have another little quiz. So we have some API, get item from indices. And we pass it some indices in that C fashion. Let's say it's a C API. And we pass it 4 indices, and we expect to get objects back, pointers or whatever. Now we call that. That's an external API we don't have the source code for. We only get 2 items back. That's clearly a bug. There's some bug in that thing, and we want to find that bug, even though it's not our code, so we can write a good bug report. We need that fixed quickly. What do we do? How do we find that quickly? Any ideas? We want to find out, so we want to find out where that goes wrong. We pass it 4 indices. It gives us 2 objects back. There must be a location where that happens.
Do you have access to get item from indices source?
No, no, no. We have to do it with assembly, but assembly code is so long, we don't want to step through it. That really takes too long. It's so hard to read. We use a data breakpoint, of course. We use a data breakpoint on that array and like go to the place where that is read. I mean, the bug must be around there somewhere. And that works. And we end up somewhere where the code looks a bit like this. So somebody reads the array and then iterates over the elements of that array and does something with the content. But we don't find that. We find that, of course. So that is ARM disassembly. Who here is more familiar with Intel disassembly than ARM disassembly? Yeah, me too. Yeah, so that's why I commented this for myself. So the first line is getting the pointer p to our array, and the second line is getting that loop variable v, and the last line is then accessing p with v multiplied by 8. That is weird, right? Because our integer is clearly only 4 bytes long. So we've already found the bug. That's the bug. They're doing the indexing wrong. Not only that, but I know that get item from indices is Windows code that has been ported to macOS. I could even tell them what the problem probably was. Because on Windows, int and long have the same size, but on macOS they don't. So I guess somebody cast that into a long and forgot about it and didn't change it for macOS. We could write that bug report and it was fixed very quickly. So that was very helpful to know a bit of disassembly and to know about data breakpoints. So now we've done the whole debugging thing. We got more bug reports, we made them more reproducible, we found the problem, and we used all the tools that we have to do this really, really quickly. We made a good plan. How do we get to the bottom of this? And used every tool we have at our disposal, learned something about the operating system. But there's one very important technique without which this is not going to work. Debugging is not working if you're not able to question your own assumptions. You clearly made a mistake. You clearly thought you were doing the right thing when you were programming this. We already know it's wrong. So now we have to question every decision we have made so far. And if you always assume that you're right, then, well, this is going to be really tough. Now that we've found the problem, we have to take a moment and think about what kind of bug is this before we can proceed to fixing it. So there are 2 kinds of bugs, I would argue. There's the kind of small bug. I would call it, you didn't write what you wanted to write. You made a small mistake. Maybe you should have used the smart pointer and you didn't, and you messed up the memory management. Maybe you forgot to initialize some variable that you wanted to initialize, etc. So you made a small programming mistake. And the fix is often a local fix. Maybe it's a local fix you can do somewhere else in your code base as well, but mentally it's a small fix. Or you made the other kind of bug. That is, you did program what you wanted to program, but you had the wrong idea in the first place. So you meant the wrong thing. Your mental model was wrong, and you need to rethink it, and you need to go back to the drawing board and find a completely different solution. Maybe you didn't understand the input data you were getting, the problem complexity you're dealing with, or maybe you didn't understand the tools you had at your disposal, how the operating system works, and what guarantees it gives you, etc. So you need to rethink, figure out a new approach, maybe. And now, unfortunately, telling these two apart is pretty difficult. So let's say we have this little piece of code. We're getting this vector of pointers, we iterate over it, we dereference the pointers, and now it crashes here with a null pointer. What do? Well, we could do this, of course. But is this a good fix? Is that a small kind of bug and we just forgot an if? Or do we have a bigger problem? Hard to say. But what would you ask if you did a little code review? You would ask maybe, where's that vector, that input vector coming from? How is that produced? Is it valid that there's a null pointer in it? Or should that not have happened in the first place? These are questions you should ask to find out, did you make a big mistake somewhere else or a small mistake here that you can fix that way? In summarizing, yes, you have to look at the bigger picture, have to ask yourself, what were you trying to achieve and how are you doing that? And is that actually the right approach? And do you really understand the problem you were trying to solve? And is the solution a good solution to that problem? And when we've done that, then we can really fix our bug. And here, people often recommend that we should write the smallest possible fix that solves the problem. Because that runs the smallest chance of introducing new problems, right? We keep the fix small, less chance of new bugs appearing. And I wouldn't phrase it that way. I would phrase it differently. Because if we tell people this, then what they often hear is smallest fix, and not smallest fix that really fixes the problem. So we might introduce fixes that don't really fix the root of the problem. Maybe they only fix one instance of the problem, and in the worst case, we miss some opportunity for refactoring and just pile small fix on top of small fix on top of small fix until our code is a hot mess. I would phrase it the other way around. Imagine you would be in an ideal world without constraints. And given everything you know now about the bug, about the problem you're trying to solve, what would the ideal solution look like if you could start from the beginning? And when you figure out what that ideal solution would look like, then maybe you can figure out how you can move towards that solution, now that you're back in the real world. So back in the real world, we can maybe say, hey, we have this stable release. We have to patch that quickly. Let's do the small fix there. But let's move our development branch towards the ideal solution, bit by bit. So our software gets better over time and maintainable and not worse. And then we have to wonder, why did that happen in the first place? How did our tools fail us so we could make that bug? Was it hard to program correctly and too easy to program incorrectly? Were we missing something? Some library feature, some helper function, an algorithm we would have needed that we tried to reinvent? And can we prevent that from happening again by introducing that missing bit that we would have needed? Can we just make that fix elsewhere in our code base? So were we missing some abstraction that would have helped us? these can take very different forms, right? So we had this in our code base, I think 64 times or something like that. So you would have some data, not an integer, because then it's really simple, some data that you want to sort. And once you've sorted it, you want to get the range of unique elements. Does anybody know or see why that would be a bit error prone? What can go wrong here? You do the sort and then a unique. Well, they use different predicates. The one uses a less and the other uses an equal, but they have to be compatible, right? Otherwise, the unique elements are not the ones you were looking for. And that's why I said we used this 74 times in our code base, something like that. And of course, in some of those cases, people wrote their own predicates and got it wrong. The equal was not, in fact, equivalent to the less predicate. So we introduced an algorithm that we could use everywhere that just takes one predicate and generates the equal out of the less. And there you go. Those problems were all fixed. Another case where you need a good abstraction because it's so hard to get right is error handling, right? This is all that you have to check when you try to open a file on a POSIX system. So you're opening a file. The success case is something non-negative is returned. There's one error case where you get an invalid file handle back, it's -1, I think, and interrupt is set. So you have to try again. And then there are all the other cases that can legitimately happen. You don't have the permission, or the file doesn't exist, etc. And then there are all the other ones, the POSIX equivalent of error out of paper, that when those happen, I don't even know what I'm supposed to do. I just want to get an error report, right? So here we wrote ourselves some error reporting handlers to make sure everybody can do error handling correctly. On Windows, there's the same. A lot of those API functions will return 0 when they have failed, and then you have to call get last error to get more error information, etc. So we also packaged that up because it's such a common pattern, right? Okay, and now we are almost done. Now we can deliver the fix, and now we are doing a lot of things that I hope everybody does already. We are documenting what we did and why we did it, and probably we're documenting why we did something in the code. And I want to point out that one very important question that comes up that documentation needs to answer is, do we still need this? If you look at this 10 years later, not only why we did this, but when can we throw this out again? You're doing code reviews, probably, or pair programming, or something else that forces you to explain your thinking to somebody else, so you notice your own mistakes before committing them. We all use version control, so we can do those things in the first place that I talked about, doing git bisect to find out what introduced the breaking change. And we do tests, hopefully, so we can prevent that bug from happening again if it was a subtle bug. Maybe we can write tests with random input, so we don't only test those few cases where we know they work, but only also cases where we don't know that they will always work. And then we are hopefully writing better, stable software that has less bugs, and ship that. Thank you. Thank you for your attention.